we converted the vector field that is the gradient vector field for x to what? The corresponding one form. How did we do it? We used the metric. So anyway, whatever. You can take it or leave it, but this is in fact an identity which we just derived, so there you go. I'm not 100% sure that's exactly the musical morphism, but I think it is. I guess that's the thing I didn't entirely cover in here either, did I? So, yeah. My apologies. Let's see here. Another example. I mean, the idea of the musical morphism is that we can use the metric, the non-degenerate metric, to convert forms to vectors and vectors to forms and vice versa, because, well, like this basically, this allowed us to convert the vector field x to the corresponding one form df. Yeah. The thing that makes this unhelpful is that the Euclidean metric is its own inverse. So, some of the things I'm starting to fuss about have to do with the distinction between the metric and its inverse metric. So, like, I can look all day long at the Euclidean metric. I'm never going to see the distinction I want to see. Anyway, here it is. Omega dx1 wedge dx2. If it was dx1 wedge dx1, that would have been easy. dx3 wedge dx4. So this is a 0, 2 tensor on R4. And he wants us to take the interior product of I with x of omega, where x is equal to x1 partial 1 plus x2 partial 2 plus x3 partial 3 plus x4 partial 4. You'll forgive me, I'm using the notation partial I is partial xi, which I think is a good notation for things like this, right? And I would encourage you to use that notation as well, so you don't go nuts. Now, the easiest way I know to do this is just to straight up write omega as what it is, which is dx1 tensor dx2 minus dx2 tensor dx1 plus dx3 tensor dx4 minus dx4 tensor dx3. See, because remember, we have this identity that like alpha wedge beta is equal to alpha tensor beta minus beta tensor alpha, supposing that alpha and beta are one forms. Right? So that's how to convert from one form. And that's easiest to do here, because then when you look at I hook omega, it's easy to see that Ix hook omega is going to be equal to what? See it like dx1 of x dx2 minus dx2 of x dx1 plus dx3 of x dx4 minus dx4 of x dx3. But what is dx1 of x? What is dx2 of x? What is, that's the first component of x, right? So what is this? Is x1 dx2 minus x2 dx1 plus x3 dx4 minus x4 dx3. Would this have been helpful, Cooper? Yeah, so sorry. But you figured it out, so I guess the rest of you, procrastination for the win, right? So you got me. It's not the lesson I was trying to teach you, but Oh, well. Now, what's that? It's the lesson you always learn here. Yeah. Maybe you have a future in engineering yet, Sam. Let's see here. It's not a compliment, Travis. Take after your dad? Yes. I guess that's not too bad. Let's see your proposition 4.6.19. I lost my chance to take after my dad. I didn't use my math major as a catapult to getting into medical school. Let's see here. Oh well, lost my chance. But my mom, what's that? Still got time? My mom taught me from an early age, don't be a doctor. People don't respect doctors. Is that why you're Dr. Cook? Well, what she didn't realize is that in the future people wouldn't respect professors either. So, jokes on my mom, I guess. But sorry. But yeah, if people call me Dr. Cook, it just makes me think like I'm not my dad. But let's hear I of x. Listen, 1, 2, and 3 are all about the fact that the interior product is linear and you can pull smooth functions out of it. I'm not going to write those down. You can read them. Part 4 of the proposition is interesting. It says if we take the interior product of a wedge product with a vector field x, then we get kind of a product rule. You shove the x into the alpha, just like you'd expect. You wedge it with beta, fine. But then something funny happens. You get a -1 to the k, alpha, wedge, the interior product of beta with x. So we get this graded Leibniz rule, just like with the form. With the exterior derivative, that happens. And also, the interior product plays nice with pullbacks and push forwards. So like the interior product of x of the pullback of alpha, well, guess what? It is the pullback of the interior product of y with alpha, where y is what? Indeed, it is the push forward of x. Very good. So I guess if you write it without the y notation, this looks like what? The push forward, right, of I of the, pullback rather, of I of the push forward of x of alpha. So if you don't invent this y symbol, it does look a little bit mysterious, but that's actually how it goes. Not a conservation of stars in that equation, I'm sorry. But a star is born. Let's hear, yes?
How is the value of k determined in this situation?
Indeedly doodly. What is k there?
Is that when you switch the
Here, this is a k form. It's the sign that it costs you to bring past the x's. So if you think about alpha wedge beta, it's an anti-symmetrized product of alpha and beta. And to get the x over to the beta slots, you got to move it past the alpha slots. So like
alpha slots can have k.
Alpha is assumed to be a k form in this equation. Yeah. Yeah, it's exactly like that. That's right. So, I see I have spent foolishly too much time on my jibber jabber about Yang-Mills stuff earlier. My apologies. Indeed there are. So that brings us to section 4.7, which is on the Lie derivative. So what's that?
He keeps smirking at me.
I am not, that is in your mind, is in your mind, but now it will soon become reality. Let's see here. The Lie derivative. That was my best smirk for the moment. Let's see here. So I'm just going to put the definition down, and I'll talk about the ingredients here. So we have T and RS tensor field on Rn. All right, and X, a smooth vector field. All right. And here's the thing that you might have forgotten about with flow, but your homework that you're doing right now will help you remember this. Flow phi sub t going from Rn to Rn. Then, given all these toys, the Lie derivative with respect to x of t is denoted L sub x of t, and it is defined to be d dt at t equal to 0 of phi sub t pull back t. Now, why does this make sense? So this phi sub t is the flow, right? For a smooth vector field, this is a diffeomorphism. So we can calculate the pullback of a form along the flow. And so just generically speaking, what you're doing here is you're looking, maybe this is t equals to 0, this is t, right? You're comparing t at 0 and t at, well, this is horrible notation. You're comparing t here to t here, anyway. And this is a flow line of what? Of x, right? So calculating this derivative is accounting for how the tensor is changing along the flow line. And essentially, you could look at it as this: t prime is t plus dt. That's the wrong thing to say. This is a lie, but maybe delta t would be better. I don't know, something like this. The point is that this is actually still a tensor of the same type. But this is actually the change in the tensor field in the direction of x, accounted for as a tensor again. Now, you can, I'm erasing the evidence. Let me just get straight to how this looks like. Properties, it's linear, you can pull out constants. 4.73, you've got this, the Lie derivative, Lie derivative at x of the tensor of two tensors. Guess what it is? It's the Lie derivative at x of s, tensor t, and this one has got no signs. S tensor, the Lie derivative at x of t. So if you're looking for a notion of differentiation which doesn't change the object type, this is the one to go with. Right, yeah, much like the derivatives back in Calc 1. This is very much not what an exterior derivative does, right? But there's this delicate interplay between the Lie derivative, the interior product, and the exterior derivative. This is all wrapped together in something called Cartan's formula, which I'll write for you in a minute. But before I get to that, I need to share a couple other fun facts with you. Nothing would make me happier than to spend 3 hours like carefully working through every line in this section, but I don't think it's actually that interesting. Really, we just want the theorems from this section to go forward. And I'll try to assign an appropriate homework problem so that you can kind of appreciate it better. But 4.75 here, we get that the Lie derivative, I keep doing that. I'm trying to use that L, not the other one. The Lie derivative in the direction x of a vector field y is given by xy minus yx. Now this we also denote as the commutator. That's composition of vector fields. Generally speaking, you'd worry that that would give you you might worry that that wouldn't give you a derivation back again. Are second derivatives derivations? Try this out. What happens when you take d squared and you let it act on the product fg? What do you get? You get yourself an f prime prime g plus a 2f prime g prime plus a g prime f g prime prime. What you'd like for it to be a derivation is that it's d squared acting on f times g plus f acting on d squared g. I mean, like that. But you notice what happened. Oopsie, this guy. So his second derivative is not a derivation. And yet I'm claiming, I told you that the Lie derivative produces another object of the same type. So if that's true, this should again be a vector field. This is actually a vector field. The reason is the piece which is offending, it's balanced out. Because you have both directions that offending term cancels. I will feel guilty about something I'm doing right now and come back and add more detail next class, but let me just get to the really interesting formula so we can stop for today. There are other properties. Proposition 4.7.6 gives you a few fun facts here that are almost immediate from the above formula. The Lie derivative of x with x is what? What's the change in the vector field along itself? It's 0. Yeah, 0, right. You might guess 0 or 1, but this time 0 is still a vector field, so 1 is not, so you know your choice is clear. On the other hand, what happens if you say, but what about the change of y with respect to x? How should these be related? What's that? Negative, right, yeah. So if you see a train going to the right, they see you going to the left, right? Incorrect? It's like that. If the train flows right, then the train sees you flowing left in a more appropriate language, a flowy language, since this is all flows. It's all flows. One of the deep and interesting things is if you have two vector fields, you can look at a so-called flow box. You can flow along x, flow along y, flow the opposite along x, flow the opposite along y, and you may or may not come back to the same point you started with. It turns out that if the vector fields commute when you travel the flow x, flow y, opposite flow x, opposite flow y, you'll get back exactly where you started. You actually get a rectangle. But if, on the other hand, if you do this flowing along the flows, and you don't get back where you started, That's a signature of non-commuting vector fields. Viscosity would be. We'll talk more about that Friday, okay? Yeah, so in our usual experience, of course, if you do the same amount of walking one way and then the reverse way, right? Supposing that you're not, walking against a hurricane, which is like picking you up and putting you back a few steps one direction but not the other, you're going to get back to the same point, right? So the interesting thing, though, is actually that ties into some deeper manifold theory, which he doesn't talk about, which is the so-called Frobenius theorem. In particular, if you have a set of vector fields which commute, you can find a system of, if you have a two-dimensional space, all right, and you have two vector fields which commute and are non-zero, then that means that you could look at the flow lines of those vector fields as being coordinate lines, and you can actually build a coordinate system in which those appear as the coordinate derivations. On the other hand, if the vector fields do not commute like that, you can't do that. Because, well, I digress. Anyway, this is something called Frobenius theorem. I'll talk more about it next time. The thing I wanted to write down, and because this will answer some of your questions, King, but this is actually theorem. So I'll write down this theorem, then I'll make one more comment, and we'll be done for today. Theorem 4.7.18. This is really sort of the crowning achievement of this section. This is Cartan's formula. And this interlinks all these different ideas. It says that the Lie derivative in the vector field x direction of a differential form omega, all right, it's equal to the evaluation at x, the interior product of x with the exterior derivative of omega. See how that works? This gives me a k plus 1 form. This puts it back in its place, right? So I go up 1 form degree, and then I go back down by contracting with x. So I'm back to the same degree as that again. K form, so k plus 1, back to k. And then other term, plus, let's get nuts, the exterior derivative of I of x. Or you could put x in first, and then exterior differentiate, and still you'd get back to a k form. And this is Cartan's formula, which we'll look at examples of next time, all right? But here you go. This is actually the relation between these different ideas for us. We don't talk about exterior derivatives of tensors, right? We talk about exterior derivatives of forms, right? We can talk about interior products of anything, actually. You can always take a tensor and get rid of a slot by like feeding it either a form or a vector entry, You can always take a type RS tensor and reduce its type to something else by just like contracting out one of the slots with the interior product. But the interesting thing here, right, the actual use of the Lie derivative is most powerfully seen in chapter 5. That was chapter 6. I can't count. Oh, 5. Yeah, chapter 5, which is on Riemannian geometry. So, the application is we might have a metric tensor, right? And this metric tensor we're going to study in chapter 5, it's going to describe distance, all right? And so the metric tensor, though, is a type, it's a type what? It's a type 0, 2 tensor with specific properties. I mean, the one I just erased here was an example of that. That's the metric tensor on the plane. And so you could ask the question, you could ask questions like, what does it mean if the Lie derivative, what would it mean for the Lie derivative with respect to x of the metric tensor to be 0? What would that say about the vector field x? But you can start studying the change of objects with respect to this Lie derivative. So it's one of our fundamental tools for studying rates of change, how different objects compare at different points, at least locally. So I still love the exterior derivative more, I don't deny it, but I think it's easier. This whole, I mean, to talk about the Lie derivative, to really understand it, you have to really understand this whole flow line business, right? Which I think takes students a little longer to really get. Now, I've given you some homework that should help you with that. So we'll talk about it. We'll talk about flow lines again and the inner workings of the Lie derivative Friday, hopefully. And so my plan by Friday, we should be done with the Lie derivative stuff, and I should have taken at least a big bite out of chapter 5. Get us started on the Riemannian geometry is my intention. So hopefully by Friday I'll actually have another homework published. I mean, part of the reason I'm giving extensions, I haven't given you the next one to work on, have I? So, but please do the homework. I want to give you all those points. Do not despair if the grader has not given you many points yet. I will curve those later. Just keep doing them. Jess, yeah. And bribe Jess? No. Thanks, guys.